Today's lesson is on the concept of a function. By the end of this lesson, you're going to understand what a relation is and all the different ways that it can be represented. You're going to be able to identify a relation that is a function and all the different representations it has, as well as be able to generate a table of outputs given a function rule. All right, so first we got to talk about relations. And no, I'm not talking about your girlfriends or your boyfriends or your mom or your brothers or your sisters. In math, when we use the word relation, we mean a pairing of an input and an output. Usually the input is called X and the output Y when we make a table, but they can be labeled with any variables. So basically it just shows how two sets of data or information is related, right? It does not always have to be sets of numbers. So for example, I could have a relationship between the student names in my class, the students in my class, and their grade. There's a relationship there. You have a student, they have a grade. We can also have a relation between a student name and their hair color. So a student has a hair color. So it doesn't always have to be math, but oftentimes, of course, it is. Another example might be the relationship between the radius of a circle and the circumference of the circle. All right, so let's talk about how we can represent relations. Okay, so there are several ways that we can represent a relation. We're going to talk about the six most often used. And the first one is in words. For example, I can describe the relationship between the number of candy bars I buy and the cost by simply saying each candy bar costs $2. So there I'm relating the total cost and how many candy bars we're purchasing. The second way to represent that very same relation could be with a table. So in this example here, let me pull out my laser. In this example here, the X would be acting as the number of candy bars we purchase, and the Y would be acting as the total cost. So if you buy one candy bar, it costs $2. If you buy two candy bars, it costs $4, and so forth. We can also represent a relation with what we call a mapping diagram. So you might hear this be called a Venn diagram. All right, so here we have a set of inputs in this bubble, this circle, and over here we have a set of outputs. And then we draw arrows from the inputs going to the outputs to show which input is mapped to which output. So in this case, one candy bar costs $2. Two candy bars would cost $4. All right, so another way to represent a relation is with a set of ordered pairs. So we can represent an entire relation this way, or maybe just part of a relation. Here again, I've represented part of it. You can see that when we have an ordered pair, we always have first the input, or the x variable, and then the output, the y variable second. The order certainly does matter. Matters which is the input and the output. So here, remember the input's representing the number of candy bars I purchase, and the output is representing the cost. So this would be the same as the table. Look at the table here. We got the pair here, 1, 2, and then we've just written it here as an ordered pair, 1, 2, 2, 4, 2, 4, written as an ordered pair. So these are almost the same to me. Representing it as a table and an ordered pair is very similar. All right, we could also represent a relation with a graph. All right, so in this case, we're representing the relation y equals 2x because each candy bar costs $2. So if I buy one candy bar, it's going to cost $2. And so this graph would represent all possible inputs and outputs. It goes on forever. In this case, it happens to be a line, but not always. And then finally, the last way that we could represent a relation is with an equation. Of course, that is only true if both of the sets are numbers. So remember my example with student name and grade or hair color? Couldn't make an equation with that, right? I would need them both to be numbers to write an equation. All right, so now let's talk about functions. And a function is just a special type of relation. So remember, a relation is any kind of pairing between an input and an output. any order at all. It doesn't matter. So like everything could be a relation, but a function is a specific type of relation. It is a relation where each input has exactly one output. And when we say exactly one, in math we're very specific. We mean exactly one. It means it can't be no outputs, can't be two outputs, can't be three outputs. It has to be exactly one output for each input. So we can often think of a function like a machine, right? Where a machine takes in an input and produces a single output. So take a look at the diagram down below here to represent this function machine. So think here as an input, an X, a something, right? It doesn't always have to be numbers, but often it is, right? Going into the little box. Something's happening in the box. Maybe we're taking a number as an input, and maybe the box inside here, the function rule is multiplying it by 2, and then we get the single answer output here. All right, so our input, another name for that you might hear is called the domain. All right, so the input is the domain, is the X values. The output is the range, it is the Y values. So what we have to remember here are three basic things. And if you remember these three things, you're going to be fine recognizing functions when you see them, right? That every input must have an output. That's what we said there. So I can't put in an input, whether it be a number or a name of a student, and nothing comes out of the machine. That would make it not a function. Two different inputs can have the same output. So for example, I could put in the student, uh, I could put in, let's not use the student, let's use the example of the candy bars again, or something where I can put in an input like a number 2, and then I get out 4. Okay, then I can put in a different number as an input, say 1, and get out the same output 4. That's okay. It's okay that we can get the same answer as an output for many different inputs, but as long as one thing comes out as an output. And then finally, last, one input can have only one output. So you can't put in something as an input into this function machine and then the output spits out 2 or 3 or 4 different things. That's not allowed. So for example, if I put in students with brown hair as my input, students with brown hair, that's my input into my input machine, then my output would be several different students, right? Because lots of my students might have brown hair. That would not be a function, but it still would be a relation. So in short, one input, one output makes it a function. So let's practice. Let's practice identifying functions represented in different forms. So here we're going to practice identifying functions written in words, or relations rather, right? Remember relations, not all of them are necessarily functions. We're going to try to decide. And to decide that, you should ask yourself one question. What is the input? And is there exactly one output? So you're trying to identify what the input is, and would there only be one answer to that question or one output? I ask one question, I get one answer. If there's more than one, not a function, but it still is a relation. So number one here, let's think about this one. The pairing of names and social security numbers. Okay, so what's our input? What's our output? Well, let's see, what would the machine take in? In this case, the way that this question is written, it implies that the machine would take in a name. So my name, Mark Dilly. And then we would go through our database and it would output my social security number. I'm not going to tell you what that is, but it would output a single answer. I don't have two social security numbers, I just have one. And that's true of every person, right? We put in a name, they get one social security comes out. So I would say that this relation is in fact a function for number one. Okay, so I'm going to write yes or no for function or not on the screen here. So this one we're going to say yes, this is a function. Yes, it's a function. All right, so what do we think about number two? Why don't you take a moment to read number two? Pause the video if you have to. and see if we can decide if this relation is a function or not. All right, so let's go ahead and read it. The names of students in my class with brown hair. So what's the output? So it'd be like me asking the question, who has brown hair? Which students in my class have brown hair? So that's the input. That's the question I'm asking. The answer would be all the names of the students with brown hair. So is that a function? Could there be more than one student with brown hair? Well, certainly. In my classes, I typically have many students with brown hair. So if the input was hair color and the output are students' names, then this would not be a function. No, because a lot of students with brown hair. How about the cost of buying X number of candy bars? It's kind of like what we saw a few slides ago. Okay, so what's the input and what's the output? It seems like the cost is our answer to the question, how many candy bars are we buying? So see, so the number of candy bars seems to be my input. So you tell me how many candy bars you're buying, and I'll tell you how much it cost. Does that have just one answer? Let's say I said we're buying 3 candy bars. Is the output potentially 2 different costs or prices for that? No, right? You tell me how many candy bars, I tell you exactly how much it cost. It doesn't, 3 candy bars don't cost $5 and $6. Right? That doesn't make sense. It's either 5 or 6. So here's another one-to-one type relationship. One input, one question, one answer. That makes this a function. How about this last example? I want you to take a moment, pause the video, think about this one. Remember, try to identify what the input is, what the question is, and what the output is, what the answer is. All right, so how about the items in a store that cost 99 cents? All right, so there's 2 ways. It depends on how you read this question. But to me, I'm putting in the input 99 cents, that price. And then the output is all the items in the store that cost 99 cents. So if 99 cents is the input, then we get many different outputs for that, right? Because lots of things in the store might cost 99 cents, not just one thing. So remember, we can't have an output that is more than one. All right, so I would say that this one here is not a function. Now, if we switched it, if we had an item, if a particular item was the input and the output was the cost, then it's okay that I have a lot of outputs that are 99, right? As long as I get one output. As long as I don't have an item with 2 different price tags, that wouldn't be a function. But the way this one reads, it's indicating that the 99 cents is in fact the input. So into my machine would be items that cost 99 cents, and then the output would be all those items that do cost that, which could be potentially a lot. All right, so the next way that we can represent a relation, right, remember, is that using the mapping diagram. Sometimes you hear them in English referred to as Venn diagrams. And so we have inputs mapped to outputs. So here's the hint, right? You want to check to see if each item in the domain, which is the input, remember, is matched to exactly one item in the output or the range. All right, so let's take a look at this one in the top left corner. Here we have 2 being mapped to 1. All right, now here we have 3 being mapped to 1. 5 is being mapped to 3, and 7 is being mapped to 7. So notice here that each input does point to exactly one output. This 2 points to 1. This 3 points to 1. This happens to be a function. The reason why it's is a function is because it meets this definition. Each input has exactly one output. I have one arrow coming out of each of these inputs going somewhere. It's okay that I have an input, two different inputs here pointing to the same output. That's okay. But what I can't have is an example like this number 2. Look at this one over here. Notice how 2 points to 1 and 2 points to 2. So the input into the function machine would be the number 2, and then when you get two answers out for that same input, that makes it not a function. So remember, this is okay. I can have multiple inputs pointing to a single output, but what I can't have is this, a single input pointing to more than one output. So this is not a function. All right, so take a moment to pause the video and see if you can identify whether these last two here are functions or not a function. All right, so I'm looking at this one down in the lower left, and all I'm really checking is that I have an arrow coming out from each input and not more than one arrow. So really that's all I have to check. Oh, yep, that goes to one, this has one, this goes to one place, that goes to one place. So yes, a function. Okay, now take a look at this one. Notice that for the inputs 2, 5, and 7, they are pointing to exactly one output. Each of them are pointing to one output. But the input of 3 here that we have in our domain isn't pointing anywhere. So that's like it has no output. All right, so this is in fact, this is kind of a tricky one, but it is not a function. Remember, if I plug in something into my function machine, something has to come out. Nothing is not an option. It doesn't make it a function if it does that. So because this 3 doesn't point anywhere, this is not a function. All right, so that's how we can identify functions using the mapping diagrams. What about when we have ordered pairs? Okay, so remember, the first coordinate is always our input, our domain, our x value. And the second coordinate there is our output, our y value. And of course, the order does matter, right? It matters which is the input and which is the output to determine if something's a function. All right, now to identify functions from ordered pairs, it's really easy. Really, the short way to do it is just to make sure all the x values are different. Because think about it, if all the x values are different, then I don't have the same x value pointing to two different y values, or the same input pointing to two different outputs. That wouldn't be possible if all the inputs were different. Remember, it's okay if the y values are all the same. It's just the inputs. We can't have the same input going to two different outputs. So look in this first example. That's a 2, that's a 3, that's a 4, that's 6. Oh, all the x values are different, so this is a function. Second one. Let's see, just check the x values again. Let's see, -3, 1, 0, 4. Just make sure those x values are different. Oh yeah, they are. So that's a function. What do you think about number 3 and number 4? All right, so let's check number 3. I'm going to go through and I'm going to compare. I'm just looking at the x values to make it simple. 2, 3, 1, 2. Oh, wait a minute. We have a problem here because here we have an input of 2 pointing to 5, being mapped to 5. And here we have that same input 2 being mapped to 2. This is a problem, right? Because I have the same input being mapped to two different outputs, or the same input being mapped to two different outputs, so no. Right? All I did is looked at the x values and saw that I had two 2's as x values. Nope, right away, done, easy. All right, so the last one. All right, so if you said no, it's not a function, congratulations. That is not a function either. All we have to do to see that is I got a 3 and a 3 here. All right, so I have the same x value. Not a function. The only time that it could be tricky, and I don't think they'll do this to you in your checkpoints, but if you actually have the exact same point. So if this was 3, 2 and that is 3, 2, then really that input of 3 wouldn't be mapped to two different outputs, right? It would be the same point, really. So if they repeated it, that's the only thing you have to make sure that they didn't do. In general, though, you're definitely going to be safe just looking at those x coordinates and making sure they're different. All right, so now let's represent this relation as a table and try to decide which of these are functions. Right, so this is very similar to the ordered pairs, right? Because remember, this would be the ordered pair -1, 3. This would be the ordered pair 0, 3, and so forth. So when we were doing the ordered pairs, if all I had to make sure was all the x values are different, it's going to work for the table too. So go down the x values, make sure they're all different. Yes, that's a function. How about this one? Stop. I have a 4 being mapped to 2, and I have the same 4 value being mapped to a different number. No. Right, so that's why it's not a function. And then finally, 0, 1, 2, 3. So this is going to be a function. All the x values are different. It works just like it does for the ordered pairs. All right, not too bad. All right, so before I go on and talk about representing relations as graphs, I want to introduce you to something called the vertical line test. And this is how we test to see if a relation that's represented as a graph is also a function. All right, so the vertical line test states that if it's possible for a vertical line to intersect a graph at more than one point, then the graph is not the graph of a function. So let's demonstrate that to see exactly what I mean. All right, so here we go. A picture's worth 1,000 words. Let's take a look at these graphs and decide which of these relations are functions. And remember, we're going to use the vertical line test to determine if it is a function. All right, so it's what it states that if any vertical line I draw basically can only touch the graph in one spot. And if it does, then that makes it a function. If it touches it in more than one spot, it's not going to be a function. So here we have the graph of a line. And notice that any vertical line, pretend these black lines I'm drawing are perfectly vertical. See, I could draw an infinite number of them, right? But any one that I could draw possibly is only going to intersect this graph in one spot, never more than one spot. All right, so the graph of this line here is a function. In fact, all lines are going to be functions except for one type of special line. Right, can you think of what type of line would not pass the vertical line test? Hmm? So any line I draw, I think it would be pass except for one particular line, right? And that would be a vertical line. So if I happen to have a graph of a straight up and down line, then that wouldn't be the graph of a function. So if this line was perfectly straight up and down, it's not going to be the graph of a function because when I draw the vertical line through, it touches it really well everywhere. Definitely more than one spot, an infinite number of spots. Take a look at the second graph. Let's try to decide if this graph here is the graph of a function by utilizing the vertical line test. All right, well, just pick any spot to draw a vertical line and it better only touch the graph in one spot once, twice. So since this vertical line intersected this graph in two different spots, that makes this not a function. Not a function. All right, so I guess I should have wrote over here that, yeah, this is a function. Right, all lines except for vertical lines are going to be functions. How about the third graph? So here you're imagining again drawing vertical lines down, up and down this page, wherever you want, making sure that it only touches this graph in one spot. And in this case, right, it in fact does pass the vertical line test. Any vertical line I draw is only going to touch this graph in one spot. Even though it starts getting pretty steep at the tail ends of this graph, right, it's not perfectly vertical. Right? It does kind of go out. So any vertical line I draw is still only going to touch it in one spot. That's why this is a function. Pass the vertical line test. All right, so take a moment to pause the video and see if you can determine if these bottom three graphs, which are functions, which isn't a function, by utilizing the vertical line test. And so just you can imagine drawing those lines in your head and see if it touches them just once or more than once. All right, so for this one on the left here, you should have said yes. Or this is a function. Yes, it's a function. Passes the vertical line test. All right, so if I could zoom in here right around the 0, right, even though that looks like it's pretty darn vertical, it really isn't. All right, so if I zoomed in a lot more, you would see that it really is much more the S shape. So it will pass the vertical line test. How about this one? All right, so again, yes, this is also a function. It does pass the vertical line test. Any vertical line I draw is only going to intersect this graph in one spot and only in one spot. And then finally, the circle is a clear no, right? No, not a function, right? I can draw many vertical lines. They touch the circle in more than one spot. All right, so finally, let's talk about the very last way that we can represent a relation, which is with an equation. All right, now we can only represent relations as equations when both the input and the output are numbers. All right, so remember when we were talking about student name and their grade. Well, I can't make an equation that involves student name, right? I can only make these equations when both the input and the output are numbers. All right, so there's an easy way that you can take an equation, right, and check to see if it is a function. And the way that I tell you to do that for now, this is going to work just about for everything that you see, is to make sure the output variable, usually y, right, is not raised to an even power, like to the second power or to the fourth power, has an exponent that is even only on the output variable, only on the y. It can be on the x, that's okay, but not the y. Another way that you could check to see if an equation was a function was to throw it in a graphing calculator, right? Like www.desmos.com, type it in, and then see if the graph passes the vertical line test. So you could do either one of those approaches. But here I can pretty much just look at these and make sure that the output variable y is not raised to an even power. All right, so in this case, this is a function. So if it's a function, I'm going to write yes. Yes, for it is a function. Right? It's okay that the x variable, the input, is squared or raised to an even power, but the y value isn't. Look at this one here. Notice that the y variable is being raised to the second power, which is an even power. So this is no. And in fact, this equation right here is the graph of a circle, the circle that we had on the previous page. About y equals x cubed. Again, it's okay to raise the input variable, the x, to any power we want. All you're looking for is to see that that y isn't being raised to an even power, and that makes this really easy. Okay, so this is a yes, and in fact, it was the S shape that you saw on the previous page. This makes this shape. Sorry, except for it doesn't overlap like that. Y cubed. So let's see, y is being raised to a power here, so I stopped to make sure. But then it is being raised to the third power, not to an even power. So 3 is an odd number. So that's what I mean by even power, in case you were wondering, right? That the exponent is an even number. Here it's an odd number, so it's okay. That's okay. So this is going to be a function. Again, we're good here. The y value isn't being raised to any power. We're good. That's a yes. And then finally here again, this is the equation of a line. You might recognize it. All lines except for vertical lines are going to be functions. The y isn't being raised to an even power, so we're good. All right, so we're almost done here. The last thing we're going to talk about is generating different representations of functions. Say, given an equation, can you make the table? Can you turn the table into a graph? All right, so when we have a function here, y equals 2x plus 3, remember the x here is the input. So it goes into our function machine. And then our function machine does some math to it. In fact, what does the machine do according to the order of operations here? I would take whatever number that x was, multiply it by 2, and then add 3, and that's how I generate my output. All right, so in this case here, to figure out what the output is when x, or the input, is -2, I simply replace the x with -2, work out the math following the order of operations, and get the appropriate output. So the work here that I would be doing to see what the y is, I'd say, well, the y value is equal to 2 multiplied by -2. See how I just took that -2 and replaced it for our input, because our input we're going to let be -2. And then add 3. So I'm going to work this out, and we're going to get our answer here. So 2 times the -2 is -4, plus 3 is -1. Right, so see how I'm generating this table. So now we have the ordered pair, -2, 1. So we can do this for all the rest of the values in the table here. I'm going to take turns. I'm going to plug in -1 in for x. All right, so then now y would be equal to 2 times -1 plus 3. All right, so I work that out. That's -2 plus 3, which is a +1. When I plug in a 0 for the x value, y is equal to 2 times 0 plus 3. And 0 plus 3 is 3. And then finally in the bottom one here, y is equal to 2. Plug in the 1 for the x. So 2 times 1 plus 3. And this is 2 plus 3, or 5. All right, so here we took the equation. We generated a table of values. I could turn this table of values into ordered pairs, and then I could use that to go ahead and graph it. In fact, I really don't need to have the ordered pairs to graph, because to me, this table is like the same thing. I mean, they look different, but they're the same. So here I'm going to graph the point -2, -1. All right, so on my graph here, here's -2, -1. I'm going to put a point. Here's the ordered pair, -1, +1. So I go back -1, up 1. Now I have the point 0, 3. So when x is 0, y is 3. I got a point there. And then finally, when x is 1, y is 5. So I have 1, and 1, 2, 3, 4, 5 on this graph. And then notice here that we do in fact have the graph of a line, the equation of a line, a table of a line. We can go ahead and connect all of these now with a line if we wanted to. All right, so all these things are really representing the exact same relationship or function. Why don't you take the moment to pause the video and see if you can generate the outputs for these inputs given this equation. All right, so go ahead and check. Make sure you're following the order of operation and watching your signs, and check to see if you get the same answers that I do here. When I plug in a -2 for the x, I get +6 minus 2, which is 4. I plug in -1. -3 times -1 is +3. 3 minus 2 is 1. I plug in a 0. -3 times 0 is 0. Minus 2 is -2. When I plug in a 1 for the x, I get -3 minus 2, which is -5. Then we can go ahead and plot these points onto our Cartesian coordinate plane. And you might recognize this equation already as being the graph of a line. You're going to get real used to seeing equations of lines written in this way. All right, and so let's go ahead and plot some points down, draw the line. All right, so here we have -2, 4. Well, there's a point. Remember, we're going left and right first. That's the x. And the y is up and down. All right, so now we have the point -1, 1. Okay, here's -1, 1. 0, -2. There's that point. 1, -5. X is 1, y is -5. 1, 2, 3, 4, 5. All right, so there's our points. You can see they make a line. They do line up perfectly. All right, so if you're watching this recording asynchronously, make sure to go back and answer the questions associated with this video.